currently works as a logic designer in Rochester, Minnesota, and is an IBM Quantum Ambassador. As an ambassador, he is specially trained to provide clients with an introduction to quantum computing. Tonight, we are privileged to have him here to teach us and give us some hands-on experience. So, George, please take it away.
Thank you, Brian. Okay, so this presentation is it's a special presentation. The slides are strictly controlled, so I was not able to share the slides beforehand with the audience. But again, we are allowed to record and be recorded for a presentation, so there should be no problem with getting your hands on the information that you'll see here. Let me read the prepared abstract that goes with these slides. For almost 40 years, quantum computing has intrigued scientists and non-scientists alike with its possibility of solving problems that are intractable for classical computing. Over the last 3 years, IBM has made real quantum computers available via the cloud so that clients, students, and researchers can begin to learn and experiment with this new mode of computing. We'll see what use cases are being considered in industry, the state of quantum computing today, and how one can get on the right track, the right path, to make the easiest and earliest use of this rapidly evolving technology. So next slide, please, Brian. Okay, so let's discuss the motivation for quantum computing. Next slide. Okay, a little historical picture. This is from May of 1981, when IBM and MIT hosted the Physics of Computation Conference. There are many famous personages in this photo. Just to the right of the tree, if you go about 3 people over from the tree, you'll see Nobel laureate Richard Feynman. He's standing with his arms folded. And on the very far left, sitting down in the photo, that's Freeman Dyson. I don't know if you know this, but he passed away February 28th of this year. So the point of this conference was to consider the physics of computation, and there's partly a plug here for IBM, in that there are many IBMers in the photo, and they also jointly hosted the conference. I like to compare it to that famous photo from the Solvay conference in 1927 that has Einstein seated at the middle, and then a host of famous scientists standing and sitting with him. Okay, so next slide, please. Okay, so in about early 1980s, Feynman is quoted as saying, "I'm not happy with all the analyses that go with just the classical theory, because nature isn't classical, damn it, and if you want to make a simulation of nature, you'd better make it quantum mechanical." Okay. So there are many problems that we try to solve in nature that are now have a quantum mechanical basis, and it turns out that they are just intractable for quantum compute, for non-quantum computing, for classical computing. Next slide, Brian. We'll see an example of that. Okay, so this slide shows why quantum computing will have, we hope will have, it does have, superior computing advantages over the classical computing. The classical bit is either 0 or 1. On the right-hand side, you see a sphere. It's called the block sphere, and it's a geometric representation of the quantum state space for a single qubit. You'll see there's a psi there with a strange sort of bracket notation. That's pronounced ket psi. You think of it as a vector in a complex 2 space, or actually as a point on the complex, on the sphere here that you see in 3 dimensions. The 2 parameters, the angle theta that it makes with the z-axis and the angle phi that it makes with that its projection makes onto the xy plane with the x-axis, determine the state of the qubit. So it turns out that there are, as opposed to the classical case where you can only have a 0-1 value, in the quantum case, your state is anywhere on the sphere here. I would just point out that don't be fooled by the geometry of the sphere. It's not the traditional 3 space that you're familiar with. For example, points on the sphere that are orthogonal to each other, or that have an inner product that's equal to 0, are actually diametrically opposite or antipodal on the sphere. So your notion of right angle gets distorted significantly. Next slide, please, Brian. So this is an example of the kind of problems that you run into with respect to trying to solve quantum mechanical problems on a classical computer. Currently, it's impossible to completely represent, let's say, the ground state energy for caffeine in coffee on today's most powerful supercomputers. However, you can do it with 160 qubits. Next slide, please. So how many bits do you actually need for caffeine? So we needed 160 qubits, but you need approximately 10 to the 48 bits to represent the energy configuration of a single caffeine molecule at a point in time, okay? This is somewhere between 1 to 10% of the total number of atoms in the Earth. So you can see that when we say that it's an intractable problem for classical computing, it's not just something that's for the present that might be solved with classical computing in the future. The number of bits is just extraordinary. And so we have to try and tackle this problem from some other point of view than the classical one. And since nature is quantum mechanical, the natural choice is to try and do some sort of computing based on quantum mechanics. As an example of how one can expand their understanding of computing, I would ask you to consider a problem called the minimal surface problem. So imagine you have a wire, okay, and you bend it into a loop, okay, a simple loop. And you're asked now to find the surface that has that loop as a boundary to it, and you want the surface to have minimal area. How would you go about and solve that problem? Well, this problem is, it can be solved mathematically. And it can be solved with a classical computer. It's a very, very difficult problem to put into the computer and to program and to try and solve. Okay, but it's very simple if you use a fact of nature, which is that a soap film will span such a loop, a wire loop, and the shape of the soap film is naturally a minimal surface. So if you use Mother Nature to solve your problem, you can do it and get a lot more intuition very quickly by exploiting that fact, as opposed to trying to use, a computer program on a classical computer. So this is the same type of idea that is behind trying to use quantum mechanics as a basis for computing. Okay, let's go to the next slide, please. Okay, so quantum computers tackle problems in entirely new ways, leveraging some basic quantum phenomena, namely entanglement, superposition, and interference. It turns out that it should be more adept at modeling physical processes of nature. It will allow one to perform significantly more scenario simulations that you might think of trying to solve a problem in finance, okay, with regards to that. We need to point number 2 on this slide. Point number 1, well, I can give you an example of a very interesting problem that we hope to be able to solve with quantum computing. I'll get back to that in a minute. Number 3, obtain better optimization solutions. So whenever you have a solution where you're trying to optimize, maximize the amount of money that you would invest in a portfolio, or, for example, minimize the area of a surface, or of a traffic route that you've had to take. And number 4 would be find better patterns with AI and machine learning processes. Because of the very large state space that exists in a quantum computer, it makes it a very attractive form of computing for generating what's called a feature space and searching for patterns in the feature space to solve artificial intelligence or machine learning type problems. How about the next slide, please? Okay, so here's just a quick list of potential use cases for quantum computing. We have chemical simulation, scenario simulation, optimization, and AI machine learning. This is just to expand on the previous slide, okay? The example that I would like to mention as a very significant problem would be trying to improve on something called the Haber-Bosch process. The Haber-Bosch process is perhaps the most famous process in chemical engineering. What it does is very simply stated as manufactures ammonia. However, the process is very energy intensive. You have to work at maybe around 3,000, a very high pressure, 3,000 psi, and a very high temperature, 800 degrees Fahrenheit. And it turns out that that this process currently uses somewhere between 1 and 2% of the entire energy output of the world. So it's got a huge carbon footprint. What do they use ammonia for? Well, for fertilizer. It turns out that roughly half of the nitrogen, it's estimated that roughly half of the nitrogen in our bodies came from the Haber-Bosch process. So if we could try and do this process of creating ammonia or nitrogen fixation more efficiently, we could save a lot of energy, reduce the carbon footprint, and take a process which is very energy intensive and make it almost trivial. How can I say almost trivial? Well, it turns out that Mother Nature performs nitrogen fixation at basically 1 atmosphere pressure and almost room temperature. Basically, bacteria and microbes in the soil do this for us. They use, it's called the nitrogenase enzyme problem. They do this somehow with this enzyme, and we know it's done, and we've tried to duplicate it, but with current computational limitations, we just haven't been able to solve it yet. This is an ideal problem for a quantum computer to try and solve. How about the next slide, please? Okay, this just gives us an example of, it's not a Venn diagram. It's what you call an Euler diagram. Give you an example of the type of problems that we feel that a quantum computer can solve handily. All right. So the quantum possible is the dark blue there, and you'll see that the applications include quantum chemistry, materials, machine learning, optimization, simulating quantum mechanics, and you'll notice there's a little sort of just off the center. It says factoring. I would just like to point out that there's an algorithm for factoring primes due to Peter Shor, which came out in 1994, and it gives a very specific and important example of illustrating that there are problems that quantum computing can solve exponentially faster than classical computing, at least at this point in time. Why are we interested in factoring primes? Well, it turns out that RSA encryption is essentially based on the difficulty of trying to factor large numbers into their component primes. It's very easy to multiply. It's called, this is the so-called trapdoor type function or process. It's very easy to multiply numbers together, but it's very hard to find factors of large numbers, the prime factors of a number. Right now, the best classical algorithms and classical computation is roughly exponential. It is exponential in the let's say the number of bits that you need to express the number. So a large number requires exponential amount of resources, either hardware, time, however you want to try and measure it, to factor. And this is what keeps things like the RSA encryption scheme feasible for security purposes. Okay. Turns out that Shor's algorithm, which he proved in 1994, demonstrated that with a quantum computer, one could factor it in roughly n cubed, where n was the number of bits in the integer. So it's an exponential speed up. We've gone from essentially an exponential amount of resources to factor a number with classical computing to polynomial time computing with a quantum computer. And this strong result generated a lot of interest and gave a lot of impetus to trying to develop quantum computing. How about the next slide, Bob? Okay, so what do we see for a future timeline for quantum computing? Well, IBM likes to use the term quantum advantage as opposed to, let's say, quantum supremacy. Up to from the early 1900s, the foundation of quantum mechanics through 2016, we could call that the quantum science portion of the road. Basically, you establish the fundamental theorems, the building blocks of quantum computing, and right now we see ourselves in the timeline there from about 2016. We see that we're in what they call the quantum ready stage. This is where we are trying to develop better quantum computers and also create an ecosystem and engage the world for preparing for the era of quantum computing. The arrow there says launch of the IBM Q network. That's around 2017. This is when IBM made access to actual quantum computers available via the cloud. So quantum advantage, this is the goal. And this is, quite simply put, it's commercial advantage to solving real-world problems with quantum computing systems. So when we're in the stage of quantum advantage, we would hope that we would be able to actually have quantum computers that are commercially viable and can solve problems that are of commercial interest and scientific interest. Next slide, please. Okay, now I don't know why they made this slide all such a bold font, such a big font, but they did. I'm not trying to flame anybody or whatnot with this, but it's okay. So you're on the road to quantum advantage. How do we measure progress? Next slide, please. Well, IBM has developed a metric, a performance metric called quantum volume. All right? And it's a measure of the essentially power, the quantum computing power of one's quantum computer. You may have heard, some companies might advertise, we have a 1,000 qubit machine. Okay. Well, it turns out that it's not so much important to have the number of qubits, but to have a high quality qubit. Qubits are very sensitive to noise, and if their operation and their error rate is significant, the error rate increases to points that do not allow for very large quantum computations at this point in time. And this diagram is intended to show that if you're, let's say going from 50 qubits to 100 qubits without improving the error rate, then you'll see no gain in quantum computational power. However, if you take those same number of qubits, 50 in the diagram, and you just decrease the error rate by 1 order of magnitude, your quantum volume will increase 500 times. So it's very important to have quality qubits, to have robust qubits, as opposed to the actual number of qubits. Number's important too, but right now at this stage of the game, it's the error rate and having quality, high quality, robust qubits that's extremely important. I had mentioned the sensitivity to noise. It's thermal noise, mechanical noise, electromagnetic noise, electromagnetic radiation. Currently, the qubits that IBM has been working with, the so-called transmon qubit, operates at around 10 millikelvin. So it's 10,000th of a degree above absolute zero. Outer space, that's about 180 times colder than outer space. We're running at 15 millikelvin as opposed to, the temperature of the cosmic background radiation, which is roughly 2.73 K. And there's electromagnetic shielding that we have in place. There's mechanical isolation, and then there's this very cold environment that we have to run our qubits to try and keep the noise level down, the thermal noise and the mechanical noise. Okay, next slide, please. So I'm sure you've all heard of Moore's Law. In 1965, he said that they would expect to be able to double the number of transistors per chip, so basically doubling quantum computing every year. So there's this exponential growth, and you can see that on this curve. This held true for, let's say, 62 through 65. There's a similar type of law that we are trying to follow with regards to quantum volume. Next slide, please. Okay, so the forecast for growth of quantum processing power using quantum volume is to try and double quantum volume every year. So right now in 2019, so I should say last year in 2019, we had a quantum volume of 16. In 2020, we've just succeeded in and announced a quantum volume of 32. So we're on track for doubling the quantum volume every year. And what does that mean with regards to actually achieving quantum advantage? Well, we believe that let's say maybe by 2027, maybe 2030, sometime in the second half of this decade, if we can continue to double the quantum volume, we hope to achieve quantum advantage by that point in time. That's just a rough guesstimate, but maybe 2027, 2030. So this could happen in our lifetime. Next slide, please. Okay, so let's discuss okay, thank you, Brian. Let's discuss let's go into the basics of quantum computing. Okay, next slide. Okay, so there's our friend, the block sphere again. It turns out that there are roughly a handful of quantum mechanical phenomena which we try to exploit and use in quantum computing. Okay, the first one is superposition. Okay, superposition is creating a quantum state that is a combination of ket 0 and ket 1. So in the block sphere, you'll notice that ket 0 is at the North Pole. You should think of that as, like, say, the ground state energy of your qubit. And ket 1 is the excited state. So it's basically a two-state system, and the ground state is represented by ket 0, and the excited state is represented by ket 1. Now, suppose you have a state of the qubit that's, let's say, indicated as you see in the picture there, all right, that ket psi. Well, that's roughly stating that you're somewhere both 0 and both 1. That's a very vague and can be very misleading description, but it gives you an idea of what it means to say that you're in a state where you are both 0 and both 1. Okay? So superposition is just a linear combination of the two kets. Think of a vector space of the two vectors, ket 0 and ket 1. Measurement is the action of observing the qubit state and forcing it to make up its mind and go into either the ground state or the excited state. Okay? And it will do so in a probabilistic manner that's based on the superposition, the type of linear combination you have. We'll get into that in a moment. There's quantum entanglement, which provides a very strong correlation between, let's say, two qubits. If a qubit is in one state, then you might know something about the state of the other qubit. Okay? Quantum gates perform the basic computational operations on qubits. Okay? Think of these as the quantum version of the typical AND or NAND or inverter gates from classical computing, classical circuit design. And then there's quantum interference. Okay, it turns out that the qubit can interfere with other qubit states and alter the probability of what a measurement might produce, okay, when you perform a quantum computation and you measure your qubits at the end of a computation. And it's this property of interference which allows one to come to an answer with a quantum algorithm. That's, we'll get into some detail on that. So let's go to the next slide, Brian. Okay, so basically we'll expand on the notion of superposition. You see that we can represent that it's a two-dimensional state space, so 2 dimensions. We just have 2 column vectors to represent the vectors, Ket 0 is, let's say, 1, 0. Ket 1 is 0, 1. And you can write any vector in the complex two-dimensional vector space as a complex number A times Ket 0 plus a complex number B times Ket 1. Okay? Next slide, please. So superposition is creating a quantum state that is a combination of both states represented by Ket 0 and Ket 1. A and B are complex numbers. And now there's a very important restriction to those values. A and B are complex numbers in that linear combination, and it's specified that the modulus of A squared plus the modulus or absolute value of B squared have to sum up to 1. Okay? And here's a little side note. It's not that important to understand right now, but it turns out that if you were to have a complex number of unit length, okay, so here's you have a scalar, complex scalar u, whose absolute value is 1. Then it turns out that if you multiply the original state that you had A times Ket 0 plus B times Ket 1, just multiply that state through by your complex scalar u. So now you would have UA times Ket 1 plus UB times Ket 1, Ket 0 plus UB times Ket 1. You would see that you haven't altered the probabilities at all of what's going to happen. Okay? Let's go to the next slide, please. So, what's important about the magnitude of A and B is that it turns out that if you were to perform a measurement on this superposition, A times Ket 0 plus B times Ket 1, then the measurement will force the qubit to go either to the ground state, to Ket 0, or Ket 1, and that's what you would measure. But what you see is that if you perform that measurement on the same prepared qubit, Ket psi, the same superposition, many times, that the probability that you would see a Ket 0 or a measure a 0 value is essentially absolute value of A squared. The probability that you would see a Ket 1, you would measure yourself being in the excited state of the qubit, would be absolute value of B squared. So that's one of the reasons why we had absolute value of A squared plus absolute value of B squared was equal to 1, because you want to have the sum of the probabilities to add up to 1. Okay? Next slide, please. Okay, so again, we're going to see what this has to, just expand a little more on what I just said with respect to measurement. If you're in a superposition state, for example, A times Ket 0 plus B times Ket 1, then absolute value of A squared is the probability that you will measure Ket 0 or the ground state, and absolute value of B squared is the probability that you'll find yourself in the excited state, Ket 1. Okay? Here's an example. Square root of 2 over 2 times Ket 0 plus square root of 2 over 2 times Ket 1. Okay, so A and B are equal. They're both the square root of 2 over 2. You square the square root of 2 over 2 and you get 1/2. So the probability of measuring a Ket 0 is 1/2. The probability of measuring a Ket 1 is 1/2. They add up to 1. Makes sense. Okay? That particular superposition that's there with the square root of 2 over 2's, that's actually a point on the equator. And so you can see that the nicety of the geometric representation, looks like you're sitting roughly halfway between 0 and 1, well, exactly halfway between 0 and 1 on the equator of the sphere. And so the probability that you would measure a Ket 0, a 1 value or a 0 value is 50-50. Okay. Take a look at the next superposition. Square root of 3 over 2 times Ket 0 minus 1/2 I times Ket 1. Okay. It turns out that A squared here, absolute value of A squared is 3/4. The absolute value of B squared here is 1/4. Okay. So you have a 75% chance of measuring yourself in the 0 state or the ground state energy, and a 25% chance of measuring yourself in the excited state, Ket 1. Okay. How about the next slide, Brian? Okay, so now we're going to talk about entanglement. Okay, so this is we're jumping ahead a little bit here. Now, suppose we have 2 qubits. All right, so you can't, unfortunately, it's difficult to try and have a geometric, it's almost impossible to have a geometric representation of the state space of 2 qubits, okay? It's no longer easy to represent in 3 dimensions, okay? The state space is nothing more than the first qubit. Let's say the one on the far right, it would be qubit 0, and the one just to the left of it would be, qubit 1. Okay, you just multiply them with all possible combinations of the states. That would give you your total state space for a 2-qubit system. So it turns out that a basis for the 4-dimensional 2-qubit system has basis vectors ket 0, 0, ket 0, 1, ket 1, 0, and ket 1, 1. Okay? And again, a superposition is, or a state in this 4-dimensional state space is nothing more than a linear combination. If you see the A, B, C, D's multiplying those particular basis states. And there's a condition that the sum of the squares of the moduli of those of A through D has to equal 1. Okay? So what is entanglement in this system? Take a look at the first example. You'll see that it's possible, if you suppose you were to measure the qubit that's represented there furthest to the left. So you got 0, 0. Suppose you measure that qubit that's got a 0 there. What state could the other qubit be in? Well, according to that, the representation, that superposition, the qubit just to the right of it would be either a 0 state or a 1 state. So basically, there's no correlation between the value of the first qubit and the value of the second qubit. But now take a look at the 2 states below that. Those are entangled states, okay? Let's look at the one on the right first, okay? It's that square root of 2 over 2, 0, 0, plus square root of 2 over 2, 1, 1, all right? Suppose I measure one of the qubits and I get a 0 value. Well, it turns out then that the other qubit had to be a 0 as well. Has to be a 0 as well, okay? If I had measured a 1, then I would have had to measure the other qubit as a 1 as well, because there's no combination of a 1, 0 appearing in that superposition state. So there's a very strong correlation between those 2 qubit values. You measure 1, whatever value you get is precisely the value that you're going to get on the other. If you were that the other qubit has to be in the other state that it's in. Look at the one now just to the left of that example, the 0, 1, 1, 0 example. You have square root of 2 over 2, 0, 1, minus square root of 2 over 2, 1, 0. Okay. Let's say you measure one of those qubits and you get a 0 value. The other qubit must have the opposite value. Okay, if you measure a 0, then the other qubit has to be in the 1 state. Or if I was to measure a 1, the other qubit would have to be in the 0 state. If you're in that particular type of superposition. That's what quantum entanglement is. Okay. Next question, please. Not question, slide. Again, a little bit more discussion about entanglement. So there you see that it's possible to factor out a ket 0 in that quantum state at the top of the page. You can factor out that ket 0, and you see that you cannot factor anything like that in the 0011 qubit state. All right. So the second, that 0011 state that you see there is an entangled state. The other state is not entangled. And basically it's this ability to whether or not you can factor out a state into simpler components that determines whether or not it's entangled, okay? Next slide, please. Okay, so here's how a typical quantum computer would operate, okay? We have gates to perform various types of operations on the qubit state space, okay? So we start and we read from left to right. This kind of notation, by the way, is pretty much standard in the industry and in research. This is exactly the type of notation that's used by the IBM composer. So it's don't think that because you're learning some sort of graphical interface that you're wasting your time in the long run. No, you're not. You're actually becoming familiar with notation that's it's essentially universally used. Okay. So how does a quantum computer operate? You start at the far left. Let's look at just the top half. Q0, Q1, Q2. We have 3 qubits. They all start out in the same space, the same state, the 0 state, the ground state. And then you have some gates that get applied to each one. The H stands for a gate called the Hadamard gate. It operates by, if you think of that blocks here, Ket 0 is at the North Pole. You apply the H gate, and it winds up moving the ket, the vector, rotating it down to a point that's on the equator of the block sphere. One of those 50-50 type of situations. So after you apply those 3 Hadamard gates, essentially you have along those 3 wires, those 3 quantum wires, you actually have a total of 8 states being represented. Basically, you have the 0, the 50%, 0, 50%, 1 state multiplied times itself 3 times, and you wind up getting 8 different states simultaneously. This is quantum parallelism. And then you would see that little pink meter that represents performing a measurement operation. And then you would do another sort of gate operation. You see those 2 H gates there. And then at the very end, you see another set of measurements. And then you would see what you get at the output. The Q0 output, it turns out, could be a 0 or a 1. Same thing with Q1, but Q2 has to be a 0 state. All right. And something similar is happening in that circuit that's at the bottom of the page there, with Q0 and Q1 being initialized at some arbitrary ket psi 0 and ket psi 1. Okay. Next slide, please. Okay, so interference. This is so you've already seen quantum parallelism, all right? That I briefly alluded to it in the previous slide where I pointed out that by starting out in the 0 state, applying those Hadamard gates, we found ourselves going from essentially a quantum state, which was 0, 0, 0, to all of a sudden simultaneously having 8 states. Basically, you're multiplying, each superposition of 0 and 1 times itself 3 different times for the 3 different qubits, and you get 8 possible states being represented simultaneously. Okay, that's good. This is quantum interference, and this allows one to essentially add and subtract the probabilities of those coefficients that are in a superposition, that are in that linear combination. You can make, hopefully, some probabilities, some of those amplitudes, okay, larger than others, giving them a greater chance of occurring when you perform a measurement. And by doing that, you take that state space that's now consisting of many more states than you started with. Basically, you had n qubits. You'd have a state space that's 2 to the n states. And by quantum interference, if you've written your quantum program correctly, you will have created hopefully just 1 state with a significantly larger probability than all the other states. So when you perform a measurement, you would see that state occurring more frequently than any other results from a measurement. And that would be, hopefully, if you've done the algorithm correctly, that would be the answer to your program, to your algorithm, the solution to your problem. So you should think of waves. This is the quantum interference. Think of constructive and destructive interference with multiple waves being added together, a superposition of waves. Next slide, please. So notice that, okay, some operation's been performed on your quantum algorithm, and you notice that the probability amplitude of the red has all of a sudden dipped below the axis. It's the probability amplitude is not the probability. The probability would be what you obtain when you square the probability amplitude. That's why it's okay to have a negative value here. Okay. Next slide, please. The next step that you would perform all of a sudden sees all the amplitudes of the 8 qubits, 7 of them are significantly smaller than the one that's in red. Okay, so if you perform a measurement, you would a sequence of measurements, let's say 1,000, one with 1,000 times, you would see a significant amount of 0, 1, 0 measurements than as opposed to all the others, and that would be the solution to your problem. This is actually the a graphical representation of the of what's called Grover's search algorithm. I should point out that this is we already discussed the importance of Shor's factoring algorithm for factoring primes. Well, it turns out that there's another important algorithm in quantum computing that's called Grover's search algorithm. Not to be confused with anything from Sesame Street. It's much more non-trivial than that. But basically what it will do is allow one to search a non-structured database much more efficiently than a classical computer. So for example, suppose I have n elements in an unstructured database, and I've got something in my hand that I want, a copy of the information that I want to try and locate within the database. All right. With a classical computer or with a classical algorithm, what's the best you can do? Well, worst case is you would have to open the first box, check, no, that's not it. The second box, that's not it. In the worst case, you'd have to open, get to the nth box, and there it is. So you've opened n-1 boxes to try and find the element that matches what you're interested in. Okay. So on the average, it would take a classical computer, through an unstructured database with n elements to try and search through it. It takes roughly n over 2. Okay, searches. Grover's search algorithm can do the same search in square root of n searches. So it's a quadratic improvement in the computational speed. Okay, next slide, please. So here's where we talked. I mentioned that if you had a n qubits, then the resulting state space that you would work in could be 2 to the n. There was exponential growth. Well, here we'll just quickly see that. Here you have 1 qubit. You've got a 2-dimensional state space. It's got that blocks here. Okay, next. If you go to 2 qubits, well, now you just see that you can have up to 4 basis vectors. Next slide. And again, if you have 3 qubits, now you're in a 2 cubed or 8 quantum states. In general, n qubits, 2 to the n states are represented by your qubits. Okay, next slide, please. Okay, so we just went through a lot of material. I mean, if you don't understand it the first time through, don't be alarmed or surprised. Richard Feynman, who I had mentioned, the Nobel laureate I had mentioned earlier, whose quote I essentially started the presentation with, he also is quoted as saying, no one really understands quantum mechanics. So it's a non-trivial subject, and it's one of the reasons why it's non-trivial is because it's not at all intuitive. It's like our brains are hardwired for classical computation and not so much for quantum computation. Just one last little note I would like to mention. You know, in that block sphere that I mentioned, you should think of it too as that rotates in space, you know, around the z-axis. So there's not only is there, you know, like position away from the z-axis, that angle theta, but there's also a rotation that's going around, and that's called the, you know, that angle, the other angle there, phi, that's called the quantum phase. And it's basically that quantum phase that allows one to have quantum interference. Okay, enough said about that. Let's go for something a little easier, some eye candy here. Let's talk about some of the hardware. Next slide, please. Okay, this is called the chandelier. It's what goes into the refrigerator that gets your temperature down to like 15 millikelvin. Next slide, please. Okay, at the very bottom of the chandelier, you can see that on the left-hand side with that white arrow pointing to that little shielded area, that little cylinder of shielding is for to shield it from electromagnetic radiation. That's where the qubits actually reside. That's the coldest part of the refrigerator. Next slide, please. And here you see the chandelier being encased in the actual cryo tank, the refrigeration tank itself. Next slide, please. And that's the what it looks like as it's sitting in the labs at the Watson Research Center. Okay, you can see how it's mechanically isolated. It's essentially suspended from the off the floor, and it's like I said, it's 15 millikelvin at the very bottom of the tank. At the top of the tank, it starts at, you know, go down from room temperature all the way down, dropping to 15 millikelvin where the qubits are located. Okay. Next slide, please. Okay, this is a cleaned up version of several of the quantum computers that we have at Yorktown. I would just mention that at Rochester, okay, we are involved in the room temperature electronics that run and communicate with the qubits that are at the bottom of the cryo tank. So that's how IBM Rochester. We do not have a cryo tank at Rochester yet. We hope to have one someday. But that's how IBM Rochester is involved in this. Next slide, please. Okay, so using and writing software for IBM Q quantum computing systems. Next slide. Okay, so this is the IBM Q experience. It's quantum cloud services and software platform that are offered by IBM to essentially run quantum programs on actual quantum computers. Next slide. So there are three components to the IBM Q experience. It's actually called IBM Quantum Experience now. There's the circuit composer, which is that graphical interface. You've already seen illustrations of that when I was talking about how a quantum computer works. You know, start out, initialize your states, apply your quantum gates, and then measure at the end. Next slide. Okay, there's Qiskit is the more sophisticated type of programming language that that researchers will write code in. Actually, you can create and run off of Jupyter notebooks your code. Okay, and then the third slide, next, get the third column there. It's a very nice experience using this the IBM quantum experience, in that everything is saved that you created and run, and all you have to do is relog back in if you had to leave the quantum computer and come back to it after you finish dinner or whatever. Okay? Next slide, please. There are, tons of advanced programming tools for serious researchers and developers, okay? First of all, if you're not so serious, even if you have open access to some of the smaller IBM computers, okay, maybe up to 16, 14 qubits, 5 qubits, okay? If you actually join the IBM Q network, then of course that's going to require a contract, etc. But then you would have access to some of the more premium and larger quantum computers. Next. Here's an example of the Q Composer, which I hope to get to in a couple of minutes. But you can graphically build a quantum circuit, run it, and see what happens. Okay. The reason you can perhaps see why it's called Composer, it's because the quantum wires that run from right to left resemble like the staves of a compositional score. If you're interested, if you know if you can read music. Okay. Next slide. And then there's again another. You can there's tons of documentation and services, videos, etc., that will help you learn and become familiar with quantum computing. You don't have to have anything in your background except maybe a little linear algebra. Even that, they give you a reference for linear algebra. Okay, next page. And this is the Qiskit software stack. This is what interfaces with hardware. It's open source. It's Python, and you can see there are various Ignis, Aqua, Air, and Terra are the basic parts of this stack, and it's again open source. You can contribute, you can join the Qiskit community, etc., and it allows you to have access to very sophisticated programming. Next page, please. Okay, so what is the IBM Q network? I just talked about the IBM Q experience. The Q network is IBM's attempt to try and build an ecosystem of users and researchers to become familiar with quantum computing. Next page, please. So the point of the network: accelerate research, develop commercial applications, promote education, and prepare for quantum computing. Next slide, please. You can just see the various industry partners, the way the IBM Q network is broken down into industry partners, hubs, members, startups, and academic partners. Okay. Next slide, please. How do you engage in the IBM Q network? Next slide, please. Okay. Start your journey, quantum journey today. Okay. IBM Q, just go out to the website, read, try out the Q experience, try creating and running some circuits on an actual quantum computer, learn about Qiskit, and then next step would be, if you're interested in pursuing it in a more sophisticated research or business-oriented environment, join the Q network. Next slide, please. Okay, so what do Q network members get for joining the Q network? You get access to the most advanced systems and software systems that IBM has on the cloud. You get training, support, and consulting, collaborative use cases with research and design, research and development, and businesses. And you become part of the IBM Q network community, which gives you access to a wide range of skills. Okay. Next slide, please. So becoming familiar, becoming educated in quantum computing, quantum starts here. That should be almost the last slide. Next one. And final. There you go. So that's the end of the presentation. That's the chandelier that we actually have a mock-up of it. I don't think it's 100% accurate, just to prevent, try to keep some proprietary knowledge, secret. But it's basically what it looks like, and it is to scale, and it's carted around in a semi to various big events like Consumer Electronics shows or research meetings. Thank you very much. So that finishes the presentation. Are there any questions about that part of the IBM Q presentation?
This is David Holmes. I do have a question for you. So the one piece that I'm really missing is, I don't want to say a recipe, but some guidance on the best way to formulate problems. So I understand QBOs, the other, kind of the other approach, but can you give some guidance on how to formulate problems so we can think in that direction about even if it's a useful process?
That's an excellent question, Dave, but how should we say, there's the rub. Hopefully, when I show you the IBM Q experience, I can point you to documentation, which has lots of examples, and hopefully you'll get a feel for how to start or formulate correctly a problem. Sometimes it's easier than others. For example, if you're trying to do quantum chemistry, then there are a lot of algorithms already written to facilitate putting together experiments to, let's say, find the ground state energy of simple molecules like lithium hydride, beryllium hydride. I think those are two that IBM has worked on, hydrogen molecule, etc. So if you're doing quantum simulation, it's easier to set it up than it is to say, let's say, try to solve tackle a problem in material science, where you'd say, how do I go about developing a metal that's lighter than steel yet stronger than it? I hope that answers your question. It's part of the problem of quantum mechanics and quantum physics, is trying to get a feel for what's going on.
Thank you.
Okay, sure. And let's see, conceptually says, I see a question here from Tori. Says, conceptually, are quantum gates and normal digital gates the same? If not, how do they differ? Okay, they are not the same. You can think of a quantum gate as, think of the blocks here, and think of basically rotating or changing the position of the state that you're in to another point on the sphere. That's how a quantum gate would work. Quantum gates, one of the biggest differences is that quantum gates are reversible. Okay, every quantum algorithm can be reversed and go backwards. Okay, you can't do that with many digital gates. For example, okay, an inverter you can, but take an AND gate. And suppose you got a 0 at the output of an AND gate, 2-input AND gate. Well, what were the inputs? Did you have 2 zeros? Did you have a 1 0? Did you have a 0 1? That kind of information is lost in digital gates, in a digital gate, but it's not lost in a quantum gate. Hope that answers your question. Let's see, William asks, are the online quantum computers coupled to classical computers to allow for simple arithmetic or other classical programming as part of a quantum project? Excellent question. The answer is, we are working on that. The quantum simulators, there's a quantum simulator out there which does have that feature. For example, it will allow you to do a measurement on a qubit, and based on the result of that measurement, do some other type of gate operations, quantum gate operations on other qubits, type of like conditional type of operation. This is a very important ability to be able to hook up the quantum computing aspect with classical conditional type of computation, and we can do that with a simulator. It's easy, of course, because a simulator is just software emulating the behavior of the quantum gates. But to actually have that engineered in to an actual quantum computer, that's not there yet, but we're working on it. Good question. Okay, well,
I had one more for you, George.
Sure thing, Dave.
So we've got these qubits, and this is coming from our past discussions.
Okay.
How are they written and read?
Okay. Well, basically, let me describe the kind of qubit that IBM is using. It's called the transmon qubit, and basically it involves it's like an LC circuit. So think of an LC circuit where the wiring is superconducting. So there's no resistance. So imagine you've got a parallel plate capacitor, and you've got a charge on one of the plates, and you've got some superconducting wire connected to the other plate, which has no charge on it, and there's a switch, let's say. You throw the switch, what's going to happen? Well, the charge is going to oscillate back and forth between the plates, and it will do so infinitely often. It won't stop. I mean, you might say, well, isn't it emitting electromagnetic radiation? And the answer is it may, but the great thing about a quantum version of such a circuit is that it has a ground state energy from which it cannot go any lower. So it will oscillate back and forth like that in its ground state. And now, how we communicate and alter the state of the qubit? Basically through microwave radiation. Basically, we'll send in EMR, and the qubit, as I pointed out, is oscillating, right? So the idea is to try and set up a microwave that's coming in, EMR coming in, that is of the same frequency. So it's maybe a very small signal, so it's not going to, overpower the qubit in a sense, but it's going to set up a resonance. And you allow that EMR, that microwave radiation, to interact with the qubit, and over time, the resonance will accumulate to the point where it will change the state of your qubit. For example, taking it from ground state to an excited state. Does that help?
And then how is it? So that's how you'd write it. How do you read it?
You do it essentially the same way. Basically, you will interrogate it with microwave radiation, and it's sort of like an indirect interrogation. You will have you'll send in a microwave, and it will be reflected back to you. It'll come back to you, but it will be, let's say, out of phase from the wave you sent in. And whether or not, and the phase difference that you see depends on the degree of the phase difference depends on the whether or not the qubit that it bounced off of or reflected off of was in the ground state or the excited state. So that's how you read it out. Very good question.
Thank you.
Yep. How is the interference controlled, or can it be controlled? It is controlled. There are gates that, so I mentioned that, so by quantum phase, it's that rotation around the z-axis, okay? So notice that if you rotate around the z-axis, you're not changing the distance from the equator or from the poles of your qubit. So you're not changing the probability that you would measure if you were to measure it, that you would measure as a 0 or a 1. So what are you doing by changing or rotating that qubit around the z-axis? Well, basically you are changing its phase or its sign, okay? For example, if you're on the equator, you could be at ket 0 plus ket 1, all multiplied times the square root of 2 over 2. By applying a z-gate, you will change the relative phase of that pair of that qubit superposition, and you can change it so that it goes to ket 0 minus ket 1. So you've gone from ket 0 plus ket 1 to ket 0 minus ket 1 by rotating the phase. And all of a sudden you see, oh, that minus sign. So it's possible, I won't go into any more detail than that, but this just, by applying the microwave radiation ideas that I just briefly tried to describe earlier to answer Dave's earlier question, you can perform this rotation and change the phase of the sign that's present in the superposition. And from there, you can see how you could implement a constructive or destructive interference. That's the best way I can describe it. So again, it's controlled by, again, microwave radiation applied at a correct frequency. So in the time that remains, does a qubit have free will? Insofar as we know, yes, it does. That is that it is, when you measure it, it is probabilistically determined just by its coefficients of the coefficients that it has in the superposition. That determines the probability of whether you will measure a 0 or a 1. It's interesting that you should mention the free will aspect. I shouldn't go into it, but there's some very famous experiments that have been done to try and determine whether or not the qubit is actually statistically sound, or there's an experiment called the Bell experiment after John Bell, an Irish physicist who proved his Bell inequalities actually demonstrated that that our knowledge of the behavior of quantum states is especially entanglement does indeed violate our intuition, and to try and create these loophole-free Bell experiments, they have actually taken radiation from quasars that are a billion light years away and used that to generate quantum states or the randomness and compare it to what you would measure a qubit with. To actually, they had a worldwide quantum game that they asked people to play, and the results of the participants were funneled into servers, and again, they tried to determine whether or not there was a violation of the Bell inequalities. And it turns out that the Bell's inequalities and the innate anti-intuitiveness of quantum mechanics were upheld once again. So when did Professor Conway die? When did that happen? Was that recent? I said that's for Maurice. April 11th. Wow. See, and Freeman Dyson died February 28th. Okay, so we have a little time. Shall we try out ask Brian to try out a couple of examples on the IBM Q experience?
Yeah.
Okay, great. Let's try it. So Brian, if you could bring up the, okay, great. So first of all, Brian, let's click on some of those menus on the left. Yeah, okay, click on the results. So let's look at the tools. Okay, so this is a tool that basically shows the history of your results. Okay, let's go to the next one. The circuit composer. So this brings up the circuit composer, and you should be able to choose, for example, choose new circuit. Okay, this is just a little update. Okay, so there we are. There are the quantum wires, the quantum gates at the top, and we're ready to try and create some quantum algorithms or circuits. So go on down. We can go back to the far left again, and just yep. Let's look at the Qiskit notebooks. Okay, so maybe it's going to take a while to load it, but there are very many Qiskit tutorials that are presented in the format of Jupyter notebooks that you can use. Okay, so it could not load the notebooks. That's okay. We can go down to the next one on the resources. Let's take a look at the resources. Okay, they've got Learn Quantum Computing. You got the Get Started. Go to Learn. Okay, look at they have various types of instruction. They have a textbook for linear. They have a Python textbook, a linear algebra textbook, quantum mechanics course that you could go and I think it's by Professor Susskind at Stanford. So there's tons of documentation, and then let's go to the last. It's easier, more circuit composer, field guide to quantum computing. Tons of documentation for you to spend time trying to understand and learn about quantum computing. Okay, so let's go back to the circuit composer, and let's see if we can put together a simple circuit. All right, so the first thing I'd like to do is just put grab a measurement, a symbol, that black symbol under operate, and just put it right there. And now click on save on the right, unsaved changes. Just save that at the right, top right.
Oh, I think I've got it.
And just save it, yeah. Okay. And now click on run. No, you're doing great. Click on run, and now just choose. Oh, wait a minute. That was a little fast. That's okay. We had a choice, and if you click on the left hand, okay, so you can either run it on the simulator, or you can actually choose a machine, an actual quantum computer to run it on. Let's just run it on the simulator now, okay, because it's much quicker and we get results very quickly. So simulating in 1,000 jobs, 1,000 shots, as they call it, is very quick. I think we've already submitted a job. Let's see if the results are back yet. So just scroll down. Okay, yes. So what should we see? We're in the ground state. We've measured it. We should see 100% zero. So just click on that and see what comes up. Okay, so you go down. There's details. It's the original circuit. And there you are. Yep, zero. I mean, the qubit that we're measuring is actually the one that's represented by the zero furthest to the right. Okay? Okay, so let's go back to the composer. And let's now insert an X gate just before the measurement. So an X gate is like an inverter. It will, so save it and submit a run to, please. Thank you, Brian. And so now when this runs, what should we see now? Well, what that X gate does is it rotates from the Q0, the vector, it's rotating it around from the North Pole to the South Pole. Okay, and the rotation is is about the x-axis. Let's see what we got. So this should read 100% 1. Yep, we see that the qubit furthest to the right, that's the one that we were working with, is actually a 1 value. Okay, good. All right, let's go to the circuit again, and now replace that X gate by an H gate.
What do I need to do to get rid of it?
Okay, upper right-hand corner of the gate. I'm sorry, go back to the turquoise gate. Yes, click that X. Got it. Now if you can grab an H. Perfect. Save it and run it. Now the head of our gate is going to rotate the North Pole down to the equator. And so when we measure it, we should see 50% 0, 50% 1. Exactly, look at. And the simulator actually emulates noise in the qubit. So even though this is this is being run on a classical computer, there's no noise actually present that's going to affect our results. It's sort of built it into the simulation. And we see that, yep, about half the time it was 0 and half the time it's 1. Okay, how about going back to our circuit again? Okay, I'll tell you what, don't change it. So go and click on the left-hand side there. Go to the brackets, just underneath that, yep. Okay, this will show you the circuit written in code, okay? That's called QASM or Open QASM, QASM, Quantum Assembly Language, okay? Not Qiskit, but QASM. Okay, so go to the next one below that. It's really showing you essentially the answer without actually having to run it. Okay? I mean, what you'll see here are, you see, they're at, half of them are at 0, and half of them are at 1, and you see what the output state finally is. Okay? Click on the very bottom one, so leave that and go to the, yep, right there, yep. And it just gives you the timestamp. Now what's nice is go up to and click on inspect in the, not there, I'm sorry, close that up and go to the top line and you'll see inspect right after edit. Yeah, so now this is something new, it's called the inspector and it will show you the state of your algorithm at each point, as it goes through each gate. So we're furthest to the left, so go up there and click on the one to the right there. It says, yes, yeah, exactly, click that. Okay, and that shows you what you would get if you, well, it doesn't look quite right. It's all zeros. Go back again. Can you click that further? Now, it doesn't look like that's quite right. I wonder if we saved it properly. So that's okay. Maybe we'll be able to show that in the next one. So close that up. Close the inspector up on the right there. There's that X. And now what I want you to do is, okay, close up the visualization so as we can maintain or create a little suspense here. Let's drop another H gate next to the H gate that you already have there. Yep. And save that and run it. And this is going to illustrate one of the tenets, one of the really anti-intuitive type of aspects of quantum mechanics. And that is that the idea that you can be in a state, a definite state, okay, but your results can still be probabilistic. Now, when we had one of those H gates up there, we ran it, and we saw that we got 50% 0, 50% 1 when we performed our measurements. Okay, the H gate had rotated ket 0 down to the equator, and whenever we perform a measurement, we get a probabilistic result. So you ask yourself, well, that could be just like tossing a coin. So let's put another H gate there. If it was like tossing a coin, then when we run it, it should still be 50% 0, 50% 1. Okay, you're just tossing the coin again. But we don't see that. What we see is that we're at 100% 0. And that's because you're in a definite state, and it turns out that the H gate is its own inverse. Remember that question we had about the difference between digital gates and quantum gates, and I said it was reversibility? Well, it's like that the H gate can be undone by applying it to itself again. All right, it's its inverse. It's like applying an inverter twice. They have a buffer. Okay, so but what happens? It takes that 50% 0, 50% 1 type of state, the equator state, and puts the the state back up to the North Pole to ket 0. Okay? So what we've done is we've seen superposition. That's what that H gate illustrated when we were like both 0 and both 1 energy states. We've seen how we can undo superposition with just applying the H gate again. And well, in another minute here, let's do entanglement. I would like you to see some entanglement. So what I'd like you to do is remove that H. That's, yep, good. Just remove that. And then now drop down the S. Take that gate right there. That's called a C naught, and put it right next to the H. Yep, right there. Perfect. Save that and run it. Okay? Please. Still pending. So the idea is now that we're going to get a state that's one of the Bell states that's ket 0 plus ket 1, ket 1. And you'll see that here. Whoops. Oh, I'm sorry. You didn't measure the other. I'm sorry. I forgot to tell you to put another measurement on the second qubit because we want to get the joint. Exactly. Thank you. Save it and run it again. I see there's a question there from William. It said, so initially it tilts an angle 90 degrees, and then the second H gate, well, the second H gate, it's not really a 90-degree tilt, okay? It's actually a sequence of 2 rotations, essentially about an axis that's like 45 degrees in the XZ plane. And you wind up doing that rotation twice, and it actually undoes, you know, it winds up, when you do 2 H-gate rotations like that, it does another 90 degrees, but the rotation is such that it flips you back up to the North Pole. So it's not quite it's not quite a minus 90 tilt. It's the same tilt, but 2 of those rotations cancel each other out. That's the way to think about it, William. Okay, so let's take a look at our results here and look at what we see. Look at the 2 qubits furthest to the right. You see they are 0, 0 or 1, 1. This is an entangled state, okay? If I measure one of the qubits, thank you, Brian. If I measure one of the qubits, then I know the value that the other qubit has to be, okay? All right, so I'm a little bit over time, but that's what I wanted to show you. I hope that you have enough skill now to try. Let me do one more thing. So if we could go back to the circuit composer, one more thing. So go to that C naught gate, okay? And go to the upper right-hand corner. See, okay, click on that. See, so you can monitor. This is a little something that you might not see right away. Took me a while. But you can, in the C naught gate, what does it do? It turns out that qubit 0 is what's called the control bit. And the bottom with the plus, okay, that's the target of your control. That will perform an X gate operation based on the value of the control qubit. So control qubit Q0, you see it's got a C by it. If that's a 0, it does nothing. If it's a 1, it performs an X gate operation on the target qubit, which was qubit 1 here, okay? And now change the target. Just drag the target down to qubit 2. So go to, and just drag it. Click on the left-hand side by Q1 and drag it to Q2. That's it. Got it. And now go back to your circuit. Yep. See, so now you've changed the target qubit, okay? So I hope that little extra little tidbit there helps. And notice that if you go up to the right-hand corner there, which says Instruction Glossary, click on that. And here it will tell you the instructions behind the various gates and what they perform, okay? And they got a nice picture. So look at, there's the H gate that we were talking about, okay? So see, it's a different kind of rotation. And it turns out if you do 2 such rotations, okay, then you wind up actually returning to where you started, okay? And you can see the control X gate, the control not gate tells you how that works, etc. So there's tons of documentation. You just have to go through it. You know, if you make it a point to create one quantum circuit every day or every other day, pretty soon you'll have a great facility with the composer tool, and you'll be able to continue on to Qiskit coding via an instruction via the Python notebooks. Okay, thank you very much, everybody. I think this is a good place to stop.